All right, so let's now look at an example of rate of change as a problem where a lot of physicists study. And this is not the only kind of problem that physicists study, but this is only one kind of quite standard problem that the physicists are interested in knowing. Okay, so in this example, what we have here is a particle moves along a straight line, and its position at time t is given by. So just as how I have expressed my understanding, then just as how I was introducing that understanding earlier, so what we have here is called the modeling function right here. So the position function at time t is being modeled by this function s of t equals 2t cubed minus 15t squared plus 24t here. And s is measured in feet and t is measured in second. So quickly, let me give and assuming that we're only the particle that we're studying here is only moving in a straight line right here. Okay, so before I go on any further into the reading of the problem right here as far as the actual question, let me get back on the board here and explain a couple of things. So think about the straight line, and we have a particle moving. So as far as motion right here, the particle can be moving that way. We can call that way as forward, or the particle can be moving this way. You see what I'm saying now? So as far as, I just want to point out that the idea now is that in one straight line already, and this is the simplest case among all the kind of problems that physicists study right there, then even on one straight line right here, on one straight path, then the particle can already have two different directions of moving. Either it's moving that way, where we maybe can call that forward, and then moving the other way, where we can call that backwards. Okay, and so that's something to be aware of. So if the position starts here, then yes, moving in that way at some time later, it's going to make some positions. And so that makes sense that position is being measured in terms of the feet and all that, all the linear distance units right there. So we measure the position here in terms of feet, how many feet away from original location. Okay, so let me now get back on the computer screen, and let's continue reading the problem further. And so now, s is measured in feet and t is in seconds. So problem A now, find the velocity. New terminology here, and I will be explaining this terminology here for anyone viewing my video. So find the velocity in feet per second of the particle at times. So there are actually three little problems in one particular question A of our current example here. So at time t equals 0. How fast is the particle moving at time 3? And how fast is, and I kind of said that even though I haven't given the formal definition of what velocity is yet, but how fast is the particle moving at time t equals 6? So these time equals 0 or time equals 3 or times equals 6 right here. What it means is that, say for example, when time equals 3, that means at that instance. So at that instance, when the particle moving and about 3 seconds after, about 3 seconds after the original point where he started out, where that particle started it, then how fast was the particle moving at that point? And that's why this is directly the application of what we have just learned throughout our general discussion, the discussion that this is an instantaneous rate of change. I don't want to find the kind of rate where it happens in an interval of time, but I want to find out how fast is the particle moving, or was the particle moving at that instance when time being exactly 3 seconds after the starting point, after when he started moving. Okay, and that's the idea right there. So back to the problem itself, there are 3 different times instance being given here. Time equals 0, time equals 3, and times equals 6 seconds. So these are all the amount of time after the starting point. And yes, you can think of t equals 0 as, technically that how fast he's going right at the instant he's starting right at the instant the particle is starting to move. Okay, and so now this term velocity right here, what exactly is that? So let me briefly explain, and then I want to leave the real good explanation for the physics instructors, for any physics instructor of yours to explain like that. But so when we were little, like second grade, third grade, if I remember correctly, then we learned about speed, okay? And yes, speed is defined by any of our second grade or third grade teacher as how fast we're going, yes? And just like that, so how fast we're going means how much distance, okay? How much distance we have made over time. So that's a division problem, or it's a fraction distance over time. But now as we grow more mature, see, and I have just pointed that out earlier when we were still reading through the description of the problem. And even on a straight path like this, as we grew older, we realized that we're not only moving in one direction. Even though we're on a straight path, we can go forward, and then at some instant we can slow down and then decide to go backward. So just that right there, going forward has its own speed, how fast we're going forward. But then as we go backward, we're making motion too. But so either way have speed, either direction has speed, but all together. So now speed, but together with direction, that's velocity. So when we starting to really study about physics right here, then the physicists went even further and being more detailed that speed combined with direction, either we're going forward or we're going backward. That's together. So speed together with velocity, together with the direction, that is velocity. So in the rawest understanding, velocity is speed, right? But speed with direction. Okay, so keep that in mind right there. And so to keep it simple, velocity truly is speed, but it just have a distance. It has direction being part of it. And so think about it. We can go at some speed, but in this direction, and we call that it's a positive. Think about this. If this way is going forward, then this is we're looking at the positive velocity to go that way. Okay. And then if that particle after some instant, if that particle changes direction and start heading back home, then we're going in. So in that way, heading to that direction, we call that it's negative. Our velocity there is being negative velocity to go that way. So once again, there's speed here, how fast we're going that way, and how fast we're going the other way. So generally speaking, it's called a velocity. How fast we're moving in the positive direction, and how fast we're moving in the negative direction. And that's why now, so speed is not the accurate way of saying that. We're looking at velocity. And so as a mathematical quantity, then velocity as a precise definition, the velocity is so I'm not going to just stay with distance over time anymore, but we're talking about change in position, okay? See? Change in position over change in time. All right. And so really, and for anyone studying calculus, starting with your point of learning about calculus, or maybe starting about that time when you start taking some, maybe you're concurrently doing some physics course, then starting out at your point where you being in physics or in calculus 1, then we're going to start using intensively or pretty extensively that term velocity instead of speed, because this is giving us a much more precise way to describe motion. And so change in position over change in time. So like that, here's position 0 because we're starting, okay? And then as time goes on, we make a different positions. So change in position gives us some distance. And then as we going backward, we change in position as well, and our distance become different, okay? And so that's why the precise version of speed, now we in a more mature understanding, it's velocity. It's change in position over change in time, okay? And so that's all the development idea. And then one more time, I would like to mention again that, so in here, And I also have already expressed this in my general discussion of rate of change. But this modeling function, it is not our job to find out why here in this class, because I want to save that for your physics instructors to explain how they come up with these equation here. So that we just simply take 2t cubed minus 15t squared plus 24t. So whatever is being given to us here, we're going to take that function as our modeling function. This function models or monitors our positions at any time t like that. Okay, so so that means at some t times later we make whatever comes out from this calculation, we make that much positions away from home. Okay, but then my point is, if you're taking a physics class, that's where you learn how this modeling function came out. But here we're going to take the step after. Once we've done getting our modeling function, then we're going to find the rate of change right out of that, the velocity right out of that. Okay, so just now I have explained earlier, velocity is the change in positions. Okay, change in positions. Delta S, change, the difference in S, because this is position, and the formula I just erased earlier. Velocity is change in position over change in time. Okay, so in short, symbol is like that. But now, as I also mentioned in the general discussion of rate of change, then now starting at our level here, being the calculus students, then we no longer talk about the kind of interval, the kind of velocity, the kind of rate of change that takes place in one finite interval any longer. Anytime we hear the term rate of change, we refer to, so this is rate of change. Okay, this is rate of change, yes. But back to what I was saying in the middle of saying, then rate of change, we refer to the instantaneous rate of change. Okay, the kind of rate of change that only happens at one particular instance. So instead of having an interval being given here, we only have one particular point given. And so this is rate of change of positions over time, right? And yes, in physics term, we call that as the velocity. But now, the truthful meaning I want to push everybody to, anyone watching my video, is that velocity as a function. Now it is the derivative, our s prime of t, because as I have explained earlier, now anytime we hear the term rate of change, we have to automatically understand at our level, at our majority in math, then this rate of change is only precise when we're taking the instantaneous rate of change. And so just simply the term rate of change, we refer to the instantaneous rate of change, unless being specified that it has to be an average rate of change. And so being an instantaneous rate of change, that is the general derivative function. And so now we are definite of what our goal is. And so now one more look into the question. So the question was looking for the velocity, right, of the particle at time t equals 0, t equals 3, and t equals 6. That means, in other words, I'm simply, or maybe let me use the other board. That just means once we have found our velocity as a general function, which is the other way of understanding, it, s prime of t, then we just simply want to find v at 0 time. Or in other words, s prime at 0. So that's one part of our problem. It's part A, but the first little question. And then at times 3 seconds later, after starting to move, after the particle is starting to be in motion, then we're looking for a velocity at time t equals 3. Then so that means s prime at 3. Okay, and so on. We're looking at v at 6. Okay, and that means s prime at 6. We're just going to have to calculate these 3 different quantities. All right, so now one more time, allow me to get back to my other board, and let's do some quick work right here. So we know our modeling function here, and we have now hopefully clear enough what it means by we're looking for the velocity. So the velocity is our general s prime of t. And so now, after we clearly understanding our goal right there, we must definitely find our general derivative of s, which is quite easy because our function has already been given. And then assuming that the physicists have already found this modeling function correctly for us, all we have to do is to take on the next step. So S prime now of t is going to be, okay, so all the derivative techniques we have learned throughout the quarter, now it's time for that to become useful. So first term, taking the derivative, but now in terms of t. Another way of seeing this is ds dt. S is the function and t is the main variable of the function. Okay, and so S prime of t now is going to be, first term becomes 6t squared. Second term becomes 30t, and last term becomes 24. Okay, all right, and so now that's our function. I mean, that's the velocity function. It's the function that represents our general velocity at any instant t. So it's no longer position. This is how fast our motion is going, including direction. Is that positive direction or negative direction? So all answers are going to come out in here. Okay. And so now once we've had our velocity function and we have already set for ourselves a good foundation, and let's head on to the other and get back to the other board right here to do the actual problem now. So we're looking for v at the 0, velocity at time 0. That means s at 0. And so now that means 6 times 0 squared minus 30 times 0 plus 24. Okay, and so the reason I had that simply because we already had our velocity function found right here. Or in other words, the velocity function is the general derivative of our position function. Okay, and so in that way, just a straight old calculation can come out. And so let me quickly erase the other work because I need a little more line right here. But that means all these two terms here zero out, and we're looking at a final answer being 24. So just like back in those days, we learned about speed and velocity takes the exact same kind of units. So speed, we go with what in outside of our U.S. Our American convention, and we go with metric, like say meters per second, kilometers per hour. But now, if we for students who are learning in the United States, and we go with the feet over second system or miles per hour. Okay, for your driving. So this is feet per second. All right. So what is the meaning of this value? Now, before I rush into the next problem, even though we're still in the same part A, but time 0 means right at the instant. Of course, it's probably not for human being, okay? But it's just maybe some small particle that can be that fast. But right at the time when it starts, it's already zoop going to 24 feet per second, okay? And so now, the next part of the questions are quite straightforward. Now we're looking for v of 3, the velocity at time equals 3. That means we're looking for s prime at 3. Okay, and so now that means 6 times 3 squared minus 30 times 3, okay, plus 24. Okay, and so all right, so my calculation shows minus 12. Okay, minus 12. And yes, this is feet per second. So now at this point, again, before I head into the next calculation, let's try to understand a complete meaning, the complete meaning of what this is, especially that negative sign. Because like I said, maybe for any viewer of my video who has never done any physics, then this is probably your first introduction. Because so far, it could be hard to believe why a speed can be negative at first. But remember what I said now, this is not only just speed. Velocity is speed together with direction. Okay? So we shouldn't be shocked about how we got that feet per second, because just like the earlier part, that's just the standard convention, the standard unit for measuring speed or velocity. But now, why negative 12? The negative specifically here means it's just simply the particle is going backwards, heading back to where it was. Okay, so it started out, it's just like how I was explaining earlier. If the particle started out right here, then going that way, and really we can call either way a forward, but then once we define one way as the forward, then the opposite way is going to be the negative or the backwards direction. And so if I just set a convention for viewers here that, hey, going that way is the positive, is the forward direction, then the velocity that we found earlier. So think about it this way. In the first part, v at 0 was a positive 24. That means the particle at first started, in the beginning, the particle traveled that way first. Okay? Because I call that forward. So the particle did go forward that way first. So do not assume that any particle have to go that way first, or have to start out going in a positive direction first. Nope, it doesn't always have to be. It all depends on our calculation. And the calculation all depends on how the function here came out. And how the function came out depends on how the physicist experimented it. Okay, we just take on with a function, assuming the function was modeled correctly, has been derived correctly. So once again, the 24 the positive 24 earlier means the particle started to travel that way first. Then at some instance, it's going to switch its direction and go back. That's what the negative 12 here is for. Okay? And that's why later on there will be the next part of our example, which is quite fascinating, because I did kind of say that there has to be an instance where the particle changed direction and heading back. Okay, and so now that's all I need to explain. The negative sign means that now the particle is in its motion, in its speed, but going backward. That's why we're having a negative velocity. Okay, and so now we are ready for the next calculation. Now I'm short of board space here, so I have to erase the two works here. So forgive me on that. And so now our last work here is v. Let's find v at 6. Same problem with part A. We're still not done with part A of our current example. But there are a lot that we can answer once we found the general velocity function of the particle motion. And so v at 6 is the same as s prime at 6. Okay, and that means we are calculating as 6 times 6 squared minus 30 times 6 plus 24. Okay, and again, give me a couple minutes here so that I can step over and do my calculation. All right, my calculation shows a positive 60. And again, feet per second. Okay, feet per second. And so now, as far as the sign of our velocity here, then at that instance, 6 seconds later, the particle was already changed back to moving the other direction. So when time was 6 seconds after the leaving point, then the particle was heading back to that way, because it was a positive 60 feet per second. Okay, and so I purposely brought up this example with 3 different time instances, and so that we can measure the velocities here, and for anyone to to understand, when it gets to rate of change, but specifically apply into a physics context or a physics into physics understanding, then positive velocity like this means the particle is going to the forward direction, and the negative velocity, as we saw in the earlier problem, means we're going opposite direction right there. Okay, and so for the particle itself here, one particle, and from time 0 to time equals 6 seconds, for human being, it's not such a long amount of time, but you can see that the particle has already made two different kind of things, going forward, then going backward, and switch to going backward. And switch back to going forward. Okay, and so now, this is, you can kind of sense that this particle is moving in quite a fast pace right there. Okay, all right. So now we're good for part A, and let's now head over to part B right here. Okay, so now the wording of the problem says, and I decide to keep the exact same description of the problem, meaning that's on that same modeling function we have here. This is just part B. We're trying to answer the other kind of problem coming out of this motion thing. So the particle stops moving, or another way of saying is in a rest, twice. So the particle stops moving twice. Okay, it stops moving twice. Okay, first when t equals, and we need to find out what that value is. Okay, and it's doing that again. It stops moving again when t equals some blank seconds. So we need to find out, at what are those two time instances where our particle stopped moving. Okay, and so it's about the best the wording of the problem can do, but I really have to explain about stop moving, because trust me, for any one of us here and viewing our video, you have to start accepting the idea of things that happens only at an instant. So even stops moving, because normally when we hear stops moving, trust me, in your mind you're gonna start thinking about a certain amount of time, like I already stopped moving from the time now when I stop moving to the time I start talking something else, and usually there's a little time frame, but stops moving also can happen in a very instantaneous concept right there. Stop moving can only happen at one instant. So what exactly does that mean by stop moving in one instant? The particle started to move. Move to a certain point and stops moving, and to make its way back, because it has to stop moving to change direction. That's the idea. Okay, and especially the direction to go completely opposite. And so I'm not saying, stop moving, but now in our more mature understanding in math, stop moving can only happen in very slight instance, to the point we call that instantaneous. Okay, it's just an instantaneous stop. So that stop only happened at 1 second. Not even 1 second, it's only one instant of time. Okay, but so now mathematically speaking, so all that was just the discussion for you to have a clear feeling, a clear understanding of what stops moving means in a world of infinite stimuli. But mathematically speaking, when you stop moving, that means your velocity as a function of time again, simply be equal to 0. That's what it is. Because the motion is at rest. The wording of the problem also said that the motion has to quickly be in rest. Okay, for instantaneously in rest. Here, I forgot to turn on the screen here, but the motion itself right here is in rest. And the motion being in rest means it has to instantaneously stop to change to a different direction. And that's why right at that instance being stopped, velocity has to reach 0 feet per second. Okay? And so in that way, for velocity being equated with 0, that means s prime consequently equals 0. And we already have found our s prime, haven't we? Okay, that was the famous 6t squared minus 30t plus 24. okay, as a quadratic. Now we can set that s prime to equal 0. And our goal here is to find out what are the two instances. Once again on the screen. The particle stops moving twice. Okay, first when t equals some blank seconds, and again when t equals some blank seconds. So that's what it says. That means there are two instances. So the problem already let us know. Let us know that there are two instances where the particle stops moving or doing that changing direction kind of thing. Okay, so there are two instances like that. When are those? Okay, and so now that's why we're on our way. That's how we're on our way finding it. So once we solve for t, that means once we solve for t, we have found the instances that our velocity turned 0. So that's our goal. So setting that equal to 0, and the next thing now is to solve for t. So at this point, we are brought back to a problem where anyone viewing this video have your own choice of solving it, because look at that closely. It's a quadratic equation, isn't it? Okay, my way I'm showing here on the board is not the only way. You can have your own way, whichever method that you're comfortable with. I can just briefly remind, in the world of quadratic equation, you have the choice of using the quadratic formula to solve for this. The b squared minus 4ac inside the square root, and b plus and minus that square root all over 2a right there. The quadratic formula, you know what I mean. Or you can have a factoring the methods, or you can even complete the square. There are at least 3 standard different methods right here. You make your choice on that. So whatever I go here is just my choice on that. So here I see the numbers, the coefficients are easy enough, so I'll just go ahead and factor out. I'm going to factor the 6 out and ending into a t squared minus 5t plus 4. Okay, that's equal to 0. And then so in my next step, and allow me to head on to my other board right there. So in my next step, my velocity function can be factored out further into, so I mean my left hand side can be factored into a t minus 4 times t minus 1 equals 0. And once we have successfully factored or completely factored our left hand side equation here, then we're going to produce two little equations, t equals 4, the first factor, to equal 0. And then we're going to have another equation, t minus 1 to equal 0. The 6 here cannot be set equal to 0 because the 6 itself is a non-zero. So we can divide that 6 away. So that's why we only have to worry about the expressions. Those variable expression being part of the product. That will be set or equated to 0. But these things, the constant itself, the constant coefficient itself, they will always cancel. Okay? And so that means t equals 4 after solving the first equation. And on the other hand, t will equal 1 after solving the other equation. Okay, this equation lead me to that answer. This equation lead me to this answer. Have we found our goal? Have we found our goal? Yes, we have. Ladies and gentlemen, these are the two time instances. These are the two instances where our particle quickly came to a stop to get ready to change direction. Okay? And so, well, as far as the order of time right here, then this instant came fast, right? So think about it. Here's how it kind of happened right here. But what makes sense now, and combined together with the understanding after we've done our part A, then you see when t is equal to 0. On this chart right here, I'm not saying this is a graph. It's just a picture. It's just a chart describing the situation. But at starting time, when t equals 0, the particle was moving at what positive 24 feet per second. It was a positive speed. That means the particle was moving in positive directions. Or so if we call this the positive direction, then the particle was moving this way. Okay. And then at some point, the particle, remember, at t equals 3, the velocity was negative 12. It was a negative. So that means the particle at some time instance, the particle already headed back that way. So that means there has to be a time instance t equals 1 somewhere here. Maybe so maybe it hits to here, time equals t equals 1, the particle changes its way, heading back. Okay, but then didn't go for too far, and then it switches its way back. You see what I'm saying now? So maybe time equals t equals 4, maybe it hits back that way, and then it's come back out again. And that's the idea. So the particle within a small amount of time, from t equals 0 to t equals 4 is not too far. You just count 1, 2, 3, 4, and the particle already made, and go back. Okay, and that's the kind of thing that happens right there. And so, but now at least back to what we are seeing here, then we have found the two instances where our particle came to a quick stop, an instantaneous stop, so that it can change direction. So stop doesn't have to be a lengthy amount of stop. It doesn't have to be a rest like, I need to stop to take a breath. It's not like that. In the world of things being infinitesimally small, then things can just happen at the instant, only at an instant. The next instant, it's already different. Okay? All right, so now let's look on the problem again on our computer screen and head out for the next problem. I mean the next part of the same example here. So same modeling function. Question C here is quite easy. What is the position of the particle at time t equals 10? Okay, what is the position? This is our position. This modeling function tells us where the particle is at any time instant. See? S is measured in feet and t is in second, but S here is the position, okay, at time. Okay, and so that's why, so now this question here is simply regarded as, mathematically speaking, allow me a little minute to erase this. But this question in our part C truly is only S, no prime. It's the position at times 10 seconds. Okay, and so that means I am going to use the original function. That was the 2t cube, but now I shouldn't write t cube anymore. That should be 10 cube. Okay, minus, and now I was looking at 15 times t squared, but now substituted by 10, so it's 10 squared. And you can see that I use parentheses very intensively right here to keep my substitution proper. Okay, and plus 24 times 10, and it was a positive time. Okay, time amount is positive, and so now in that way, okay, so that makes 1,000. So 2,000 minus 1,500. Okay, and that's giving me a 500 right here, and plus with another 240 right here, and that gives me. So these are all easy calculations. So I can go 740. So you are at 740 feet away. You are 740 feet away from the original point. So back to what I was explaining based on this picture. So here's here's what happens. So the particle going from 0, and at some 1 second later, it made some distance and headed its way back, and then made its way continue to heading out. And so so it's going from here 1 second. And then 2, 3, and whatsoever, right? And head out. So when it gets to about 10 seconds, it made the particle made 740 feet away from where it started. And that's the idea for you to sense how fast this particle is moving. 740 feet is a big number right here. It's a large amount to make in 10 seconds, and provided it has already done some going back and forth already. Okay. So now let's look into our next part in this example. Now, question D. What is the total distance? Okay, so this question could be a little challenge right here. What is the total distance the total distance that the particle travels between times t equals 0 and t equals 10? Okay, and so this is where I have to bring back a lot of my explanations back then into where we're doing right here, because what I have explained, and now I'm going to have to re-emphasize. Within 10 seconds, the particle did a lot of there has been a lot of events within 10 seconds. The particle started moving, going this way, and then right at 1 second later, it's headed its way back, and then 2 seconds later, because when, so 0, 1, 2, 3, and then, 1, 2, 3, 4, because the other time instance for heading, the other time instance is 4, where it's changed its direction again. And so 0, 1, 2, 3, 4, right? And then it's back out. So at time equals 4, it's head back out. And so there has been some, at least some going out, heading back, and heading back out, okay, and heading out again. So in that way, you have to think about it, the total distance. That's the key word for this problem. This total distance right here, let me unhighlight all these things right here, okay? But this total distance, because it could be dangerous that people think, why is not just the 740 that I erased earlier, but the 740 is only the distance, the position that the particle is at, being away from home, okay? But really the total distance, you have to encounter all that distance it traveled out, okay, in 1 second, because that's the amount of time when that's the amount of distance where it was, because it's going that way, and then from t equals 1, it's heading back some amount of distance. So you have to count that distance too. This is distance, real physical distance. So we have to count that. So this is distance being going backward. Distance being backward. This is distance going forward, okay? And after that, going backward, we made some more distance, okay? And that distance here, the third interval, is so there's another distance being forward again. So to find the real answer, we have to add up, find a way to calculate all these 3 little distances and add them all up. That's the total distance. So it's not simply just 740 feet right there. Okay, yes, it's 740 feet away from home if we reference it back from home right there. But as far as how much distance that particle really moved, really traveled, we have to do a careful calculation. Okay, and so in this chart of mine right here, there's another way I can break it down in a picture like this. So now it does matter with the time intervals. So on time, for time right here, from 0 to 1 second, okay, this is on the time axis. I drew this one a little too large there. So how about this is from 0 to 1, okay, and 4 seconds is here, okay. So from 0 to 1, we had some distance going backwards. So I'm using that right arrow key, heading to the right-hand side like that. And then from that instance, from 1 to 4, then we have to calculate some distance going backwards. See what I mean? My chart might be a little awkward for many viewers, but my explanation I'm trying to go here is that this right-hand side arrow is indicating in between time 0 and 1, we're going forward. And then in that time 0, of course, times always go on, okay? But in that times here, we're going in the opposite direction. And then from times equals 4 to times equals 10, okay? Then we are going this direction, okay? And so we have to calculate all of these 3 little amounts all in positive quantity, okay? All in positive quantity. So in that way, then this is at least what we can do right here. We can find out, to find how much distance that particle traveled in between 0 and 1 right here. Then we can just simply find S at 1. What's our position at 1? Take away our position at 0. That takes care of how much distance, because distance is also the change in position, but simply in only one straight path. And right now we are on a straight path. Okay, so that distance can simply be calculated, and we don't have to worry about the speed can change, low and high in that interval. It's okay, but at least the total speed in that distance there in that time interval can just simply be done by, the total distance in that interval can be done by finding the difference between time 1 and time 0, the difference in position. Okay, and once we've had that takes care of this. Okay. And then now I'm going to add to the other distance. But the other distance now is simply the amount of distance that's being from time equals 4 to times equals 1. It's how much position at time equals 4 minus how much position at times equals 1. Okay, and so now along that way you can kind of see here where I'm going for the next. So this last piece right here is, this is S10 minus S of 4. Okay, but these are all, once again, you got to keep in mind these are all positive quantity. Okay, so don't just simply cancel all these things out right there, because I have a reason to ask you for not doing that. All right, so in my next board, so time at 0 and time at 1. So S1 equals, quickly, 2 times 1 cubed minus 15 times 1 square plus 24 times 1. Okay, and so my calculation here shows that's 26 minus 15, so 11 feet right here. And then any other quantity that I have not calculated, recall for yourself that at 0, at time 0, we are at 0 cube. We actually have not calculated this as well. Right, so let's calculate it in. Right, 24 times 0, and that's all here, 0 feet. So we're right from home at home, and then when it's 4 seconds, okay, then we're looking at 2 times 4 cube minus 15 times 4 square plus, and here looking at 24 times times 4. Okay. And here I'm at some negative 16 feet. So don't worry about a negative position. Really, what does that mean by a negative position? A negative position just means here's your home, but you've gone far enough, you've gone backward far enough so that you're going to kind of like somewhere here. Okay, that's negative, the position like that. Okay, all right, so now the next one, I'm going to have to lay it down. So S of 10 that we have found earlier was 740 feet. Okay, so now the total distance we're looking at now is going to be, so this is S1 minus S0, okay, and then plus with S4 minus S1. All right, and plus now S10 minus S4. Okay, and so this is now going to be at 1, it's 11 minus 0, so it's 11 feet. Okay, for that. So it's made 11 feet in that first interval. And then from S4 to S1 right here, S1 is that, but so here's the thing. This is an explanation that I was holding earlier. Back to my board right here. Now I need to add on one more thing here. But so this interval of time right here, that difference is going to give us a negative distance, but we need to actually take the absolute value of that, because for distance, it's always going to be a positive. It's just negative because we're going backwards, okay? But so the subtraction here, simply the subtraction will give us a negative quantity. But we have to take the absolute value because it's in the end, going backwards, it's still making some physical distance, and distance cannot be negative. So now I go back to that earlier work right here and put that in absolute value. And then we're going to add that to the other part, the S10 minus S4, okay? And so now these two differences, those can be just the usual differences. But this distance right here, this difference right here, since it was on its way going backward from time 1 to time 4 like that. So that's why, but distance needs to be positive. And that's the reason why I have to go with the absolute value here. So that means on this board of mine, this part needs to be in absolute value. So S of 4 minus S of 1, the answer is supposedly, see, S of 4 is a negative 16, right? And minus S of 1, that means it's going to be a negative 27. But now we're adding with an absolute value of negative 27, okay? And that's we'll eventually make that positive, and then we're adding that to this difference right here. That was 740 minus a negative 16, okay? And so now with all that there, okay, so now leave me a minute right here to do the calculation. All right, so now calculation comes out to be 794 feet total. And yes, so it's actually more than, because my point I also want to point out that I would like to make here is that a lot of time people assume that why not just take the simple distance, the simple distance between S10 and S0 right there, and that gives you the distance. But nope, it's not the case, because we actually got some going back distance. Okay, so going back counts too. It's a distance that we count. Okay, and so that's why this answer here does look to exceed the amount of 740, because right at time instance 0, we got 0 distance. And when S equals 10, the end of our interval, then we got 740. So some people can rushly think that it's just 740 feet altogether, but nope, during that time frame where the particle was moving backwards, then we have to count that distance too as a positive distance added to that. And again, that's the reason why I introduced. So I started out showing we have to matter with these differences, but then at that point on, when we realize what's going on, then I have to go back to the formula and add in the absolute values to indicate that in that time frame the particle was moving back. So simply subtraction will give it negative answer, but it's an actual distance, so we have to put it in absolute value to force out a positive distance to count into our total sum of distances. Okay, and so that's how we solve this problem here in question D of our example. All right, and so now let's head out for the last part of our example. Okay, so here it says, find the acceleration of the particle. All right. So acceleration is the rate of change of velocity. Okay, I mean, maybe you don't have to take a physics course right now, but at some high school level, science teachers should have mentioned. So change in position is velocity. Okay, rate of change of position is velocity. But because velocity now in these days, when we're so matured, we learn that even velocity is not a constant velocity. And so it's changing all over. And so that's why rate of change of velocity is the acceleration. Okay, how fast velocity is changing or how slow velocity is changing. And also it can change in a positive way and in a negative way. And that's what acceleration is. And that's our goal. So I introduced the second derivative earlier throughout our lectures in finding different kinds of derivative, right? This is where you see your first application of second derivative right here. So leave me a minute here to erase my board. All right, so now S was given to be 2t cubed minus 15t squared plus 24t. Yes, we have already found that. We already knew about that. So our velocity function, concluding and throughout all those problems so far, is S prime of t. But now, as I have just explained, acceleration, notated by a of t as a new function. Acceleration is the derivative, the rate of change, the instantaneous rate of change. So now by default, rate of change is the instantaneous rate of change. So the acceleration of t of the particle in time t right here is the derivative of our v function, our velocity function. But now relating that to our original function, then this v prime right here, this acceleration right here is s double prime, the second derivative of our position function. All right, so now in that way, we have already found our velocity function being 6t squared minus 30t plus 24. Okay, then now our second derivative, our acceleration here is going to be as a general acceleration function, 12t minus 30. And that is our general acceleration of the function. And that is all the question is asking for. So we don't have to find the acceleration at any particular time instance. This question here simply find the acceleration, and without a specific time value, then this is just, the question is only looking for the general acceleration, and that's what we have just now done right here. So our acceleration, our general acceleration of the particle can be found by that formula 12t minus 30.